I have a cute little polar bear over there. He makes me happy. But let's look at this one. This one came from what we talked about last night, okay? I don't know anything about a pi over 5 family on the unit circle, okay? But what I do see there is I got sine, cosine, and then I got cosine, sine. And that's similar to one of the identities that we talked about, which was, helps if you got a pen there, Miss Moore, sine of A minus B. Okay, and so what we want to do is we want to use that to see if we can make it equal square root of 3 over 2. So my first angle would be 6 pi over 5 minus my second angle, 13 pi over 5. All right, well, let's do a little fraction arithmetic inside of there. That's over 15. If I was going to put those two fractions together, what would have to be true? They need the same denominator, okay? So if I give this first one a denominator of 15, what's it going to change in my numerator? It'd be 18 pi, okay, minus 13 pi over 15. And so now I can put those together. That would be the sine of 5 pi over 15. What does 5 pi over 15 reduce to? Pi over 3. And what is the sign at pi over 3? Square root of 3 over 2. And that's what we wanted to prove. Okay? So that's proving a trig identity just like the crazy stuff we did yesterday. All right? So just recognizing that what that formula says when I have sine, cosine, cosine, sine, that's sine of two things being subtracted because that minus in the middle. Okay, so all we want to do right now is talk about locating a point in both the rectangular coordinates and the polar coordinates and how it's different, okay? If you look down there, you can see it, the polar coordinate system, it's a circle, all right? We're going to graph on a circle, which is really bizarre, okay? But let's start with what we know, okay? We know rectangular coordinates. You've been graphing points for I don't know how long, okay? When you made those cute little pictures. You know, I think once you learn about negative numbers, you start graphing in the coordinate plane. And do y'all remember, did y'all do those in middle school? Where you do the dots to dots and it would make pictures and stuff. Oh, I still love those. Okay, if we get bored, we'll copy some of those and we can have fun. Okay, because I was always that person that messed up and my eye looked like this instead of what it was supposed to, you know? Yeah. Anyway, so in the rectangular coordinate system, remember it uses an X and a Y axis. Our points are ordered pairs. Okay, to get to our location, we define a space or we define a point or a space by moving over, so left or right, and then up or down. And it's also referred to as a Cartesian plane. That's just the guy who figured it out. Okay? It's like naming the pew at church. All right, I paid for this pew. So that's what we've been doing for a long time. Okay, those are the coordinates that we've been using for a long time. So what we're going to do now is switch to the polar coordinate system, all right? And in the polar coordinate system, marking a location is more like flying an airplane. Okay. We're going to always have an angle in standard position, meaning it comes from the origin. Okay. And then we're going to have what's known as a signed, S-I-G-N, so positive or negative, distance from the origin. finding our location is more like flying an airplane. Okay, we're going to go to our angle, all right, wherever it's at, and then we're going to go our signed distance from the origin, all right, positive or negative, and that's going to be a little weird. Okay, we kind of think about positive and negative as forward and backwards. Okay, so for that signed distance, positive would be forward, negative would be back. Just like the rectangular coordinate system has axes, all right, this one has what's referred to as the pole and the polar axis, right? So the polar axis is the one that would go through our anchor point, where we start, okay? So if we're thinking about like our anchor point on our unit circle, that would represent our polar axis, right? Our pole is our terminal ray. Right? Where did we stop that angle that was in standard position? Now, if we look at this piece of graph paper that's right here, you'll notice it's marked off in those angles that we know, all right, which is nice, all right? It's our unit circle. And then we have all of these. What do we call it in geometry when you have a circle, then a circle, then a circle, then a circle? It starts with a C. Remember? Concentric circles. We have all these concentric circles. And so guess what the radius is for the first circle? If it's first, it would be number 1. All right. The second circle would be 3. That's your radius. Okay, so how far out we're going to go. It's that signed distance. It's going to be our radius. Okay, so just a different looking piece of graph paper. All right, different looking piece of graph paper. So let's talk about how we're going to graph. Okay, so we're going to do some. So here's a polar axis. All right, and some points. Now, our points are always listed like this. R, stop please, comma theta. All right. And unlike rectangular coordinates, we do the angle first. Okay, so we do it backwards. Okay, so we're going to do the angle first. All right. So the first thing I want to do is to find where pi over 3 would be from the polar axis. Okay, so if I look, here's my polar axis. I would go all the way. There is pi over 3. Okay. Now, the next thing I want to do is from the origin, so from that 0, 0, I want to go out to a radius of 2. So you got to look at your circle, though, okay? It did several before it listed 1, and then it did several more before it listed 2. So on this terminal ray, on this pole, from the origin, I'm going to go out 1, 2. I'm going forward, all right? Following that, and that's my point. Okay, so that's my point to pi over 3. Okay, so we do the angle, right? And then we do the radius. All right, let's look at the next one. Okay, point B, 3 pi over 2, and then 1. Okay, 3 pi over 2, and then 1. So I'm going to start over here on my polar axis, go around to 3 pi over 2. So that would be this whole downward thing right here. Okay, but I got to pick the right circle. I want a radius of 1. And so if I go out to that circle where the radius is 1, okay, and I follow that terminal ray. Okay, so positive means it's on the terminal ray. It's on the pole. Okay, let's do the next one. 3 and 4 pi over 3. Let's start with 4 pi over 3. Okay, so think about that. Which quadrant are we going to be in for 4 pi over 3? The third. So I can find that pi over 3 line and extend it down. All right, so it would be this one. Okay. And then I have a positive radius. So I'm going to be on that ray, my positive ray. I'm going out to the third circle that's marked. And so that's C. Okay. You following me? We okay so far? All right, let's do one more. So now let's do negative pi over 6. Let me get me another color up here. Let's do pink. Okay, so negative pi over 6. So which way are we going to move this time for my angle? Clockwise, okay? Pi over 6 we know is going to be that first little division of 3 right there. Okay. I have a positive radius, so I'm going to be on this ray at the second circle. So that's D. Okay, let's add one more. Let's add point E, and let's do 5, nope, wrote it backwards. Let's do negative 2, 5 pi over 6, okay, because we've not done a negative radius yet. Okay, negative 2, 5 pi over 6. All right, rock and roll. Okay, so 5 pi over 6, which quadrant are we going to be in? Second, okay. 5 pi over 6 is that third that's closest to the x-axis. So there is my pole. Okay. Now, because I have a negative radius, okay, we're not going to be on that pole. We're going to go the opposite direction from our radius. Okay, so the opposite direction would not be on that pole, but backwards, 1, 2. So it's going to land in the same place as point D. Okay, and that's weird. Okay, a negative radius puts it in the opposite direction from the pole. All right, take a second, see if you can plot the ones underneath it. Okay. See if you can plot those. Anything crazy happen? They're all in the same place. Okay? They should all graph in the same place. All right, did that on purpose. Okay. All right. They should all graph on the exact same place. All right. Pi over 4 and then 2, that's right in the first quadrant. If I went negative 7 pi over 4, I would go backwards, all right, to that top quadrant, still a radius of positive 2. 9 pi over 4 all the way around, and then a little bit more for the 9 pi over 4, radius of 2. 5 pi over 4 is the trickiest one, so let me show you that one. If we go to 5 pi over 4, it's in the third quadrant, but I have a negative radius, so I would back up, go the opposite way. So they all ended in the same place. The reason I wanted to show you that is because how many different ways could we name that circle? Name that point? A lot. Okay, we could name it lots of different ways. Okay, so just because you have a point doesn't mean that's the only coordinate. In the rectangular system, you're 2, 4 or you're 2, 4, right? You're not 2, 4 and something else, right? You can't be 2, 4 and 4, 6. Doesn't work. All right, they're two different locations. But on that polar coordinate system, we can name the same point lots of different ways. Okay, So let's do that for a second. I have no idea why this is all blanked out right here. Okay. Whoops. Okay, is yours blanked out too? No. Nope. Okay, must have been when I transferred it over. Okay. So let's see if we can come up with 3 or 2 more ways, all right, to say this point, right? So plot it, and then let's visually see if we can think of ways that we could say it. Figure out where it's at first, and then let's come up with some options. All right, let's try it with a negative angle, okay? So if I was going to do a negative angle and I was going to go clockwise to get there, okay? -6, negative, what would that be? -7 pi over 6. That would land in the same spot. Would I need a positive or a negative radius? Positive, okay? So that's an option, all right? That's an option. Anybody use another positive angle? Yeah? What'd you use? Okay, what was your positive angle? 11 pi over 6, yep. Oh, and a negative radius, okay? If I go to 11, oh, stop that. If I go to 11 pi over 6, fat hands, okay. That would land me here, and so I need to go backwards, -3, so that works. Okay? Anybody else got something? You could do 17 pi over 6, right? We could wrap around it all the way again, all right? A whole unit circle. So you could do 17 pi over 6 and still use a positive. Let's do one more where we use a negative radius. Any ideas on that one? Yep, negative pi over 6 and a -3 would land it in the same spot. So there are lots of correct answers, okay? We cool with that, naming the point and getting there. Okay, well, like most things in math, we can connect two things that seem completely opposite from one another, okay? And so we can connect rectangular and polar coordinate systems, all right? And it's really kind of cool. It's kind of like how we married the unit circle and the right triangle, all right? So take a look. We know in a rectangular coordinate system, let me switch back, right? We have an X, we have a Y axis, we have 4 quadrants, okay? And we get to our point by going over, let's say, and up. And so this would be the point X, comma, Y. All right? So we know in the rectangular coordinate system, that's what it looks like. All right? In the polar coordinate system, all right, we start with this polar axis. We have this pole or this terminal ray, okay? We have a theta, and we have our radius, which is r, and we have the ordered pair r, comma, theta. Okay. So what I want to do now is blend those two pictures together. Okay, I want to blend those two pictures together. And so think about it this way. To graph my rectangular coordinates, I'd go over X, I'd go up Y, I'd form a right triangle. When I connect that right triangle like we had been doing, okay, we get a hypotenuse, but that's where the polar coordinate comes in. What is that the same thing as? That's my r. Okay, that's my radius. And where would theta be? Yep, it's that angle that's right there. Okay. So we can marry those two things together. The x and the y coordinate make the triangle that forms the right triangle, where we get theta and we get that hypotenuse, which is our radius. Okay. Now, from the right triangle, let's put a little trig in there. Okay. Let's put a little trig in there. We know, or we can find cosine of theta. How do I find cosine? Adjacent over hypotenuse. So x over r. All right. Can we solve for x? What would I have to do to get x by itself? Multiply by r. So x is the same thing as r cosine theta. Okay. Likewise, we can get sine from that triangle in our rectangular coordinates, which is y over r, opposite over hypotenuse. And so what does y equal? R sine theta, okay? And this is how we're going to convert from rectangular to polar coordinates, all right? X is going to be r cosine. Makes sense because on a circle, cosine is x, and we got to have the radius, all right? On our unit circle, y is sine. Got to have the radius, r sine theta. All right, so let's do a couple of conversions. Right. We'll walk through a couple of these. We're not going to do them all right, because I want us to get at least through this part. Okay. All right, rock and roll. Let's look at this first one. We'll do the first one and the last one. So we'll mark this middle one off. Okay. So right now, is it written in polar or rectangular form? Polar. How do we know? There's an angle there. All right. It's going to be a family, you know, pi over 6, pi over 4, pi over something. Okay. So we know it's polar. So to convert it to rectangular, x is going to equal r, which is 2, cosine of pi. Y is going to equal, okay, r sine at pi. So we're going to convert this to a rectangular coordinate by just working it out. What's cosine at pi? -1. So 2 times -1 is 2. And what's sine at pi? 0. Yeah. And 2 times 0 is 0. So that's your conversion. Okay. So literally all we're doing is just evaluating a trig function. Okay. So to go from polar to rectangular, that's what we're going to do. All right. Let's try the next one. All right. Again, just trying to get this new ordered pair. Okay. So x is going to equal r, which is -3, cosine at 7 pi over 6. Y is going to equal -3 sine at 7 pi over 6. Okay. Which quadrant is 7 pi over 6 going to be in? The third, which means everything's negative down there. Okay. Cosine at pi over 6 is going to be square root of 3 over 2. And so then sine's also going to be negative because it's in the fourth quadrant. Okay. The top one, all right, it's going to give me 3 root 3 over 2. And then y is going to be 3 over 2. And that's all. Are you freezing? Sorry. Yeah, I know. I don't know why it's doing that today. I know. Usually it's warm and I'm like, I don't know what's going on today. I haven't touched it. Unless my sneaky children did it while I was downstairs doing testing. Okay, so now let's talk about going the other direction. We're going to use the same kind of concepts, all right? But we're going to go from rectangular to polar, all right? Polar to rectangular is easy. We're just evaluating a trig function, all right? Going backwards, a little more complicated, not terrible, okay? We do have to use the Pythagorean theorem, all right, such that x squared plus y squared is r squared, because we're going to have to find r, all right, which is the Pythagorean theorem. And we've got a triangle there. And then, because we're going to have an x and a y, we're going to have to use tangent. So tangent theta equals y over x. Now, where we have to be careful is we got to think about our quadrants. Okay, we're going to think about our signs in Q1 to Q4. All right, so that we be sure we choose the right place. Okay, so let's do one of these. Again, these are not terrible, all right? The first thing we want to do is think about this ordered pair, okay? So negative 2, 2, which quadrant is it going to be in? Second. So I go left 2 and up 2, all right? And that's what helps me pick the right theta here in just a second, okay? All right, let's get r, all right? We know that r squared is going to equal 2 squared plus negative 2 squared, or r squared equals 8. So what would r equal? Square root of 8, and we're going to leave it like that, okay? So in my polar coordinate, my radius is going to be square root of 8. I'm glad we don't have to graph that one, okay? Now, to get our tangent, all right, we know that tangent theta from the triangle is y over x. So 2 over negative 2, or tangent theta is equal to negative 1, okay? In that quadrant, which theta would give me a tangent of negative 1? All right, which angle gives me a tangent of 1? It's the pi over 4 family. What's its name in the second quadrant? 3 pi over 4, that's my theta. Okay, so that's why the quadrant is important. Okay, that's why that quadrant is important. All right, let's do C. Okay, we're going to skip that middle one. Let's do C. All right, my ordered pair is the ordered pair 0, negative 5. Okay, and the first problem I see with that is I ain't got no triangle, all right, because I'm sitting on an axis, all right? But we can find our radius still, all right? We take x squared plus y squared, all right? So 0 squared plus negative 5 squared would equal my radius squared, or 25 equals r squared. What's r? It's 5, okay? So r is going to be 5. Now, in order for me to start and get down here, what does that angle have to be? 3 pi over 2, okay? Because the tangent would be undefined. The tangent would be y over x, which is undefined. So it has to be 3 pi over 2. That's why I like drawing the picture, all right? So I can figure out which angle I'm using. All right, question about that. All right, last thing, and this is going to sound so dumb, okay? But we can graph complex numbers in the Cartesian and the polar plane. So the only thing that changes is you have x and you have I. So if you have the order of the complex number 3 plus 2i, it is still your ordered pair 3, 2. You just have to relabel the axis. It's just weird. okay? So we treat the real number as x, we treat the coefficient of I as y. All right, that's the only thing to that, okay? Which is weird. If you've never graphed on a complex plane, it's just a Cartesian plane, and instead of y, we use I. Okay, weird, but it is what it is, okay? So if we transfer that to polars, okay, x is still r cosine theta. Y, we put an I in front of it, r sine theta. That's really the only difference, okay? That's all we do, and not the polar plan, the polar plane, okay? All right, the good news, it works the exact same way, all right, of what we just did, okay? So you use the same conversions, you graph to the right ordered pair, you do all the same things. It's no different, okay? So on this packet, all right, ones that you should look at, okay, ones that you should look at are worksheet A, 3.13, okay? We'll do the other two on Tuesday. 1, 2, 5, 6, 7, 8, 10, 14, 16, 17, and 20. Okay? So just a little practice, just the basics of polars. Okay? So what we'll talk about on Tuesday are polar functions, what makes the cool graphs and equations. And then, I can't remember what the last part is. Rates of change, average rate of change. Yep, that's what it is. Okay? Good job. Thanks for letting me hustle through that. Appreciate y'all. I thought that one was, we could get it done quick without too much stress. Okay, if you're not coming tomorrow, I need you to let me know. At least I got you.
I'm not.
You're not coming. Okay. Okay. Oh, thanks. I love it. So this gives Ms. Craddock stress because of all the redoing I had to do this week, just because of, yeah. Anyway, I look back through this and I'm like, man, we worked hard this year.
Yeah.
Makes me feel good.
Yes, I'm so glad you understand that. I'll do that, and I'm like, I feel crazy because I'm like, I get so excited, and I'm like, why am I?
Yep.